Originally, I had wanted to talk about these multiple choice practices, but I think it looks like at least half of us didn't get to it. So I'm going to just delete that page out of here, and we'll kick the can to talking about that on Thursday. Wednesday, sorry. Whatever, next class. Thank you. Yes, Wednesday. Everybody okay there? Okay, that's fine. Today, let's start. We'll take a few questions from homeworks, and then we'll start talking about 2.4 and 2.5. Okay. Talika?
Could you do number
57.
57?
Sure.
Actually, I didn't wish it. Yeah.
Just check this real quick. All right, so it's asking us to find the limit of f of x as it approaches 1 if we're told that this thing is 10. Right away, we should see that, well, I can't do a direct substitution on this because I get a denominator of 0, and that's not going to be super helpful to me. So what I want to do, is I need to get that denominator onto the other side. So what I'm going to do is like multiply the top and bottom of this by x minus 1. Now I have to do that like inside of the limit. Maybe I write it here. So when I do that to both sides, I have to do like one of these. So that stuff is going to cancel out now. And now I'm going to do my limit properties so I can kind of distribute that limit. And here, that's continuous. Or I'm sorry, is polynomial. So I can direct substitute there. So that just goes to 0, right? So the limit as x approaches 1 of 8 is just 8, right? The limit of a constant is the constant. So I'll just add 8 to both sides, and we're done. Yeah, well, here, this is the tricky thing. Like, if you don't realize that, like, oh, yeah, I can kind of do that. Like, just treat that limit as a variable. It works. Pierce.
So how do you know that, like, when you move it over to the other side, that's when you should do direct substitution instead of like doing the limit of like 10x minus 7?
Well, okay. So you could, Pierce, you're going to get the same answer if you distribute the 10 in. That's okay to do. Because when you direct substitute that, you still get 0, right?
Yeah.
So it'd be fine if you decided to do that. The fact that this is a polynomial is what's telling me that I can do direct substitution on it.
Okay.
Right? So there's, like polynomials, I can always do direct substitution on. And then rational stuff, as long as you're not direct substituting, as long as you're direct substituting to something in the domain. Right? So before over here, I couldn't do it because 1 is not in the domain of whatever this function is. I don't even know if it's rational or not because I don't know what kind of function f of x is. Right? F of x could be exponential or something. I don't know. Does that feel okay?
Yeah.
Okay. What's next? Jacob.
You do 32, please.
32? Sure. And this one probably just gets algebraically gets a little yucky. So first thing I'm going to notice is that this limit as h approaches 0. So h is kind of like my, that's what I'm going to kind of think about as my variable, and x is going to act more like a constant in this case. So my answer should have x's in it when I'm done, which is fine. It's not going to come down to a number because I have x's and h's, and h is what's going to 0. So the x will still be there. So what I'm going to do is I'm going to start by just making a common denominator in the numerator between those two fractions. That common denominator to me looks like it's just going to be quantity x plus h squared times x squared. Do you buy that? Okay. So I'm going to go ahead and write that common denominator kind of all in one shot. Is that okay with you?
Yeah.
Okay, so I'm going to have x squared minus x plus h quantity squared over x squared times x plus h squared. And then at the same time, I'm going to think about like now multiplying by the reciprocal. So I'm also going to get like an h down there. Cool?
Yeah.
All right. What I'm going to do now is I'm going to, this now looks a lot like, say, like number 17 or 18. So I'm going to try just foiling this out and seeing if enough stuff cancel out and some good stuff starts happening. So I'm going to FOIL out that numerator. I'm going to put the h over here so it's up with the leading coefficient stuff. Let's distribute that negative through now. So all these things just turn into minuses. And I notice, hey, the x squareds are going to cancel out. And now I see I do have a factor of h that can reduce. And that's great because at this point, once I've done that, when I do, if I were to try to do a direct substitution, I no longer get a indeterminate thing. So now I can direct substitute because I no longer get like 0 over 0. Oops, that's supposed to be x. So that just becomes negative 2x over x cubed. Notice at this point I've dropped the limits after I've done my direct substitution. Up until that point, though, I hung on to them all the way through. When I was looking at your most recent homework quizzes, a lot of us are dropping limits after the first step. That limit needs to stay until you do your direct substitution, or until you get your calculator out and look at a graph or something to evaluate it. When you're doing the algebra, that limit probably should be sticking around.
How do you get x cubed?
Yeah, because wouldn't it be x to the 4th?
Oh, sorry. Yeah, thank you. I think I probably, I don't know. I think I'd already started reducing it halfway through when I was writing it. If that ever happened to you, like you get a step ahead.
Yeah.
Jacob, do you feel okay with that?
Yeah.
And it, again, once you made that first step, it wasn't so bad, but like seeing that that's the first thing I want to do rather than foiling stuff out to start, you know, can get kind of messy if you try that route. Although it still would be able to get there. Pierce.
I have this curse to you. 1 over x.
Well, let's go look at. Nope, the answer I've given is the same answer as the answer keys. So
She lied.
maybe she just made a mistake. Maybe you had the wrong problem written down on your sheet of paper when you showed it to her. Believe it or not, I make that mistake. I copy stuff down wrong all the time. Like, it's such an easy mistake to make, and you're like, I can't get the answer in the back of the book. It's like, well, do you have the right problem?
That makes the difference.
Makes a huge difference, right? Okay. Anybody else on 2-3 stuffs? Rita? Sure. Yeah. Okay. This is a fun problem. Oh, that's not where I wanted that to pop in at. You found it?
Yeah. Somehow we dropped the negative sign somewhere,
Ah,
and then we also added we were supposed to.
okay. So here, this is like a classic, like a classic real analysis kind of problem. So if you are someone that's destined for, a lot of mathematics in your future, you'll run into this course eventually at some point. It's kind of your theoretical foundational calculus course. So it's all about like the real numbers. So one property about the real numbers is between any two rational numbers, you have infinitely many rational numbers. But if you try to count these up in comparison to the irrationals are like many, many more than rationals. There's a lot more irrational numbers than there are rational numbers. We call them dense, like the irrationals are densely packed in there. Anyways, so we have something like this, and we want to look at the limit as x approaches 0. If you tried to do this by direct substitution, you can't, because it's a piecewise function that's not polynomial. So what do we do with this? We have one tool that we can use, squeeze theorem. So what function would lower bound f of x? I mean 0, right? 0 is always going to be less than or equal to fx squared, because x squared can never be negative, and it'll always be equal to 0, so we're good, right? What would be a good upper bound function? Well, not 1, because like 2 squared is bigger than 1. Squared?
Oh.
Right? Infinity, probably not. Again, like,
How do you know x squared?
well, because it's always going to, x squared is always going to be bigger than or equal to 0, because it's always going to be non-negative, and
Yeah, I said like 1.
it'll either be equal to x squared, right? So we know the limit as x approaches 0 of 0 is equal to 0, and we know the limit as x approaches 0 of x squared is equal to 0. So by the squeeze theorem, the limit as x approaches 0 of f of x is equal to 0. And we're done.
How did you know that x squared was 0?
That,
Oh.
direct substitution,
Okay.
right? Just direct substitution.
Okay.
So this was the hardest part. This was the hardest part, was realizing that, oh, there's a squeeze theorem candidate. What functions are going to be my upper and lower bound on this?
I had it
No, this is a race, because I was like, oh.
Elena.
We did 6.
62? This one is just like the, yeah, this one is just like ugly algebra. This is a, can you keep track of all your stuff? Okay. So, again, first thing you probably want to check is what happens if I try to direct substitute this. You end up with 0 over 0, right? Okay. So, what do I want to do first here? What do you think? Great. Which one? Both is a great idea. I love that idea. So let's do 6x plus 2 over root 6 minus x plus 2 and root 3 minus x plus 1 over root 3 minus x plus 1. Yikes-a-rooski. All right, but it's not so bad, right? When I multiply those two together, I get 6 minus x minus 4, right? The square roots just cancel because you have the square root squared, and then minus 2 squared, right? Because it's just a difference of 2 squares. Now I still have that other factor there, and maybe we'll multiply that out. Maybe we won't. We'll have to see what we got. And here I'm going to multiply those two together. Again, those are conjugates, so just like a difference of 2 squares. And that other piece I'm just going to let hang. So far, so good. If I clean up now these pieces, what am I going to end up with? 2 minus x over 2. Yes! Cancel, cancel. Get rid of those guys. And guess what we have now? Oops. Notice that basically all we've done is we've made a reciprocal, but more importantly, we've changed those minuses into pluses. What's that going to allow us to do? Yeah. Now, keep in mind here that we're not like, technically we're not doing direct substitution. I mean, we're doing like, oh, I can use my limit laws to push this thing like underneath the radical, and I distribute the limit to this thing, because it's not a polynomial or a rational function that we're doing this to. We're going to make that part better here in a minute. In section 2.5, we're going to clean up that. But what do I end up? This is when I do my direct substitution now, I can do that. I get 1 plus 1 in the numerator. And in the denominator, I get 2 plus 1. So I end up with 2/3. Wait a minute. 2 plus 2. 2 plus 2. 2 plus 2. Oh, that's because I miscopied it. That was supposed to be a 2. That makes more sense. Look at that. See? Made a mistake. And what kind of mistake was it? It was like the dumbest mistake possible. 2 just turned into a 1 because I was going too fast. Because I got excited about the math. It's like, I see the end! Let's rush to get there. It's like, rush. That's where you do dumb things. I just did it. Pierce. Sure. Everybody okay with this one, though? Again, notice I didn't try to multiply everything out. Like I'm going to multiply by 2 conjugates, but I'm going to be picky about what I take turns multiply. Like I don't want to multiply everything out if I don't have to. Do the easy part. Stop and see what you have. Maybe something good is going to happen. It did. And then you didn't even have to worry about foiling again, which again is stinky, right? Like easy to kind of goof that up. And once you multiply it out again, the canceling that you need disappears. Like you can't see it anymore. And now all of a sudden I don't know what to do anymore. So you just went too far. You need to stop in a previous spot and take a look. Stop and look around. Stop and look around. Part of it is like we live in this GPS era where everybody knows exactly where to go all the time. And we're just not used to like just stopping and looking around to kind of see where we're at. Used to be like a normal part of life pre-smartphone. Yeah, of course. All right, it says show by means of an example that the limit as x approaches 2 of f of x plus g of x may exist even though neither the limit as x approaches a of f of x or the limit as x approaches a of g of x exists. So my initial instinct would be to try something like like f of x equals something over like x minus a, and g of x is going to equal, let's do this. What if we do that? Clearly the limit as x approaches a of f of x is going to equal like, undefined, right? So have we called this positive infinity yet? Are we able? No, this is going to be, this doesn't exist. It'll be going either way. That's good. Doesn't even have to worry about it. Right? If you graph this, you're going to have an asymptote with one end pointing up and the other pointing up at x equals a, right?
Yeah.
Like the very first day, the very first homework quiz thing we did, right? So neither of these two limits exist, right? Everybody agree? But if I look at f of x plus g of x, what is that going to give me? They have a common denominator, right? And certainly that limit does exist. So that's what I did. I just took two rational functions that were undefined at a, and I just made their numerator, so when I add them together, I get the numerator to cancel the denominator. And then that's the limit I can do. Well, I start out by just making x minus a in the denominator. Because I know at that point you're going to have a rational function that has an asymptote at a where one end points up and one end points down, which does not exist, right? At a. So that's a limit that doesn't exist for both of them, right? For if I add these two together and I want to get a limit back, the denominator needs to cancel out because that's the part that's a problem. If I can cancel that denominator out, then everything is going to be fine. So what do? Well, they already have a common denominator, so I just need, when I add the two numerators together, to get x minus a. So one of the numerators is going to be x and the other is going to be negative a. When I add them together, I have x minus a over x minus a. And the part that was the problem, the x minus a in the denominator, cancels out, so everything is good. How sneaky is that?
Really sneaky.
So again, the hard part would have been starting with knowing to start with like the x minus a in the denominator. And there's probably another way you could have done this with like something else, but this to me seemed like the simplest, most obvious way of doing this. Because like if I go back and I look at, the problems like 32, the issue is just trying to get the denominator to cancel out, right? Once I get that denominator to cancel out, like I did in this step, I can do the direct substitution and finish it. So that's what all I'm trying to do, is to build a problem where when I do the addition, I can reduce out the denominator so that like a direct substitution or to be a simple problem after. So that's kind of what I was doing. You probably could have even stolen one of the homework problems. If you took something like 23 and you just broke that sum up into two separate, the fractions like something plus something over something, just broke it up into two pieces, you probably could have used that. I bet that both of those, you'd have to check on your calculator or whatever, but I bet both of those function, or both of those limits would have been a problem also. Like, it doesn't have to be complicated. Like, it sounds really bad, right? But it's like, oh, what if I just use something I've already done from the homework and just break it up with a common denominator or something, and it turns out, oh, that works fine. Jacob.
For 59, for the proving one,
Yeah.
I just said for every like increasingly rational fraction that gets closer to 0 in its value, then the y value gets closer to 0 too. Does that work? As proof for that.
Well, that claim you're making, so the problem has to do with like the density of these two like rationals and irrationals. So like it's still going to be looking, like really bouncy, and in fact, because it's not continuous, like you're going to have like, as far as a proof goes, it's not great. Like your logic is sound, like what you're saying is true. The issue is like that rationale works well for continuous, but this is like everywhere discontinuous. Like it has infinitely many jump discontinuities. So like that intuition is like, I don't know that. I don't think it's great.
Okay.
But again, like certainly what you said was true. The issue is that you don't address the discontinuity part, right? And like what happens if it's a discontinuity immediately before you get to 0?
Yeah.
Right? Like, so it's one of these where it's like the limit existing needs to have, like if you have, this to that, like which, like if this is 0 here, that limit doesn't exist.
Yeah.
Right? So it's one of those where it's like, because we don't know exactly where the discontinuities are, where the jumps are, I don't think you can make that argument, even though what you said is true, but I don't think it can allow you to say that the limit then is going to 0.
Okay.
If that makes any sense.
Yeah.
Okay. All right. So let's talk about 2-4 here. I think we handled all the toughies there at the end of that chat, or at the end of that section, and hopefully we saw that like, oh, maybe those weren't as bad as I kind of thought.
Yeah.
But it's one of those like until I saw what to do, it was I still think it was pretty bad. But that's like when I assign some of these at the end, it's mostly a lot of time it's to get you to think about it, like to engage like abstractly with the material in a way that just like a rote, here's like a problem that's just like the other problems. It's like maybe the algebra is maybe a little yucky or whatever, but like isn't much different from the previous ones. Like a very different kind of problem to force you to kind of think about it. Because it really helps build out your intuition and makes like the no calculator multiple choice questions, I think, easier to deal with if you've really kind of thought hard about what these things mean. Anyways, continuing on. 2-4. So here we're going to be looking at the precise definition of a limit. So this is not something that would be AB material, but if you're planning on an engineering degree or something like that, it's certainly something you'd see in a 3. I would think at minimum you would do a fair bit of this kind of work. We're just going to do like a little bit of example and kind of talk about what this precise definition means and how you use it to like make a proof. But I'm not going to assign any homework from this section. I'm not going to ask you really to do anything with this, other than like sit and appreciate, kind of try to use this to like help build out some of your intuition. Okay? All right. So our definition says, let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we say the limit of f of x as x approaches a is L, and we write the limit as x approaches a of f of x is equal to L if for every number epsilon greater than 0, there is a number delta greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta, then f of x minus, or the absolute value of f of x minus L is less than epsilon. What are we saying here? So what we're saying is epsilon is the distance between the function's value as you're approaching a and the limit, right? So like if we look at a picture, if this is our function f of x, epsilon is our distance between f of x and the limit. So if I look at this problem, this is the limit, what do we have here? Limit as x approaches 3 of f of x is equal to 5, right? So this distance in here is like your epsilon. What it's saying then is that you can find a distance here, that's your delta, between the x's such that, like f of x minus delta is equal to 5 minus epsilon, and somehow we can capture that limit in between. I can find 2 x's that can capture that limit between 2 y's, or I can use the 2 y's to find the 2 x's that capture. And you can, as you kind of squeeze those down, as you make the epsilon smaller, the deltas need to get smaller, and eventually you can kind of capture the limit inside of that. That's what we're trying to do. So what one of these proofs look like then is what we're trying to do is like find the delta, like figure out what that delta is. Okay. Okay, so if I look at this, if I go back to my definition, this is my x, this is my a, this is my f of x, and this is like my L. So far, so good. So just kind of like trying to connect what we have to the notation. So we're always going to start with this piece here, the part with the epsilon. How do I rewrite that absolute value inequality without the absolute value?
equals, yeah, negative 1. 1 equals like positive 0.2.
So you can write it like this, right? If the absolute value of something is less than 0.2, that means that without the absolute value, it had to be between negative 0.2 and positive 0.2. Right? Everybody's good with that? That's like your basic old algebra. And now what we're going to do, oh shoot, look at what I did. I copied that down wrong. Right, that was a minus sign there. Is we're going to add 2 to both sides. Now when we have an and inequality, you have to add it to both ends, right? Everybody's okay there? So what I'm going to do now is I need to find the value of x where x cubed minus 5x plus 6 gives me 1.8, and when x cubed minus 5x plus 6 gives me 2.2. How would I do that? What? Let's graph it and find an intersection, right? Do I have a good way to solving a polynomial like this? No. No. So that's what I'm going to do. Now I'm going to cheat a little bit because I know where this lives. Just so I don't have there's my function. I guess we need to be a little bit more precise than that, huh? That. Why didn't I graph both of them? Oh, that's why. Dum 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 dum. Kulik. Dum da dum dum dum. That should be a 3. 2.2 is bigger than 2. You dum dum. That's why you couldn't see the other one. Okay. So if I look I'm going to look at this end. I don't think it really matters which end. I think either one would work. So I'm just going to use this side. So intersect command, enter, enter, and then, oops. So I have 1.12 for one of them. And then 0.91 for the other. Let's think about that for a second. So look at where the decimal is. I don't think I should have rounded down. Because there's values of x that are greater than 0.91 that happen before the point I've just chosen, right? So I probably want to round that to point. I always probably want to round up regardless. That should probably be 0.92. So remember where we're trying to get to now. We're trying to make this, right? Elena? Yeah.
So that one's the 0.92, which one's the 1.92?
That one.
Oh, I was thinking cross.
Okay. So remember we're trying to get to the absolute value of x minus 1 is less than, we need to find that delta. So I want to turn this into x minus 1 is less than some number. Well, how do I do that? I'm going to just subtract 1 from both sides. So far, so good. So we'll say the absolute value of x minus 1 has to be less than what? How do I know to choose that one rather than the 0.12? Because, well, you want to pick the smaller one, right? 0.08. Well, here's the thing. If you pick the bigger one, then there's values on the other side that don't work, right? If I go from 0.08 positive and negative here, yeah, I lose some values over here, but if I went from 0.12, I'd pick up things over here that I shouldn't have, right, that don't work.
Is it negative or negative? Didn't you add to
Because of the absolute value, right? I turned it into an absolute value.
No, 0.08. Because of the absolute value?
Yeah. Yeah. Because I've changed it into an absolute value. The only thing come out of it is positives, right? If I said absolute value is less than negative 0.8, well, that's never true,
Oh, yeah.
right? So remember the absolute, when I have something like this, an and inequality, I can treat it as an absolute value by dropping like the less than side that's negative and just putting the absolute value around it. So what's the delta have to be? Yeah, of course. So that's my delta. It's the 0.08. So the more common setup would be something like this. Where you're given a limit and asked to prove it. So we're going to use the definition. So remember we have x minus a is less than delta, and 0 is less than f of x minus L less than epsilon. Right? Is that how we wrote the definition? Let me scroll back. Oh, it's that way. Sorry. This was the one with the less than 0 on it. It doesn't really matter. Right, this is our starting setup. So let's fill in our values for A, which is 3, for f of x, which is 4x minus 5, and L, which is 7. So far, so good. Okay. So I'm going to combine like terms. Inside my epsilon inequality. I notice inside that epsilon inequality, there's the greatest common factor of 4. So I can like pull that out, right? Why can I put the 4 outside of the absolute value? It's just positive 4, right? So it's like, so we divide both sides by 4. And what do we have here? So what does our delta have to be? Epsilon over 4. That's it.
What do you think? Is it like a value or is it just no? It's like the range, right?
So it's like the distance between the x's is what the epsilon, or the epsilon is the distance between the y's.
Oh.
The delta is the distance between the x's. That's what we're finding.
Yes, but.
All right. That feels like that's enough of that. Okay. So let's start 2.5 then. Okay. 2.5 is about a property called continuity. Now, we talk briefly about continuity in like algebra 2 and pre-calc, right? But usually the definition we give for continuity is just like, it's a function whose curve you can draw without picking up your pencil. Something kind of like that, right? Here, we're going to give ourselves a formal definition. So we're going to start with what does it mean to be continuous at a single point? And then we're going to extend that to be what does it mean to be continuous over an interval? And ideally, we talk about continuous over an entire domain because a domain is just an interval, right? We say a function is continuous at a number a if the limit as x approaches a of f of x is equal to f of a. So if the limit evaluates out to be the same thing as the value of the function, then we'll say it's continuous. Why would that work? If you think about a function, when we say the limit exists, it means that like the left end of the function is going into the right end of the function. And if there's actually a point there, what it tells me is the left side of the function connects that point, and the right side of the function connects that point, and there's a point there, that tells me that's continuity, right? So if the left end of the function hooks in, and the right end of the function hooks in, and there's a point there, that point must have been continuous, because the function, you could draw into it, draw out of it, and there's a point there. Is that everybody's okay with that? So you can't have a jump discontinuity because both ends are going to the same thing. You can't have a removal discontinuity because the point is there. And you can't have an asymptote because the left end and the right end are going to a finite value, right? It has to go to f of a. That's not infinity. Does everybody feel okay on that? Okay. So again, this implies that f of a is defined, that is, a is in the domain of f. The limit of f of x at a exists, and then that the limit is equal to the evaluated function. So if we look at this graph here above, what values are we discontinuous at? 1, 3, 5. Great. Why? Well, let's think back to our definition of continuity.
No.
So 1 doesn't work because f of 1 does not exist there, right? Or I shouldn't say doesn't, I should say undefined. So the limit as x approaches 1 is fine. There's no problem there. That exists, and it's equal to finite value, but f of 1 is not defined there. What's the problem at f of 3? Nope.
Oh, it's like at two values, like,
Yeah.
or like they don't agree.
Yeah, the limit does not exist in that case, right? And what's the matter at 5?
But also the limit does not exist.
Nope, the limit exists,
God, how dare you?
right? Because the left end and the right end go to the same value,
Yeah,
but it doesn't equal f of 5.
so it's just not defined.
Nope, it is defined at f of 5,
Oh my God.
right? So there's a point at f of 5, right? But that value is not the same as the limit, right? The limit is going towards that value,
Oh, okay.
which is not what f of 5 is. F of 5 is way up there
Wait, how did you know that F was?
because it was a straight open circle.
Oh, okay. Wait, so it doesn't exist. So it would just be undefined close to just the open circle because it's.
Okay, you're using a lot of pronouns there, and I'm not sure what it is. Which number are we talking about? 1, 3, or 5?
5.
Okay. So the limit exists at 5 because the left end and the right end are both going to the same value. F of 5 is this point up here. The limit as x approaches 5 is this point down here. Those are not the same y value. That's why we don't have continuity there, because they do not equal the same thing. That the limit and the function evaluate out to different things. That's why.
So why could, so would 1 continuity to and just undefined?
1 is not continuous because the limit exists, it goes to this value. F of 1, though, is undefined. There is no point at x equals 1. Because if you look at this, what kind of discontinuity is that? That's a removable, right? Where there's just a point missing.
Yeah.
Elena, you're still making some faces.
What point is missing?
Well, there's no value at 1, right? There's not a filled circle at 1. Whatever this y coordinate is, say it's 1, the point 1, 1 isn't there. You'd need that point for the function to be continuous there. If that was filled in, then yes, you'd have continuity.
How is there continuity at 5? Also?
There isn't.
Oh, I thought you were saying that.
No, 1, 3, and 5, we do not have continuity.
Okay,
They're
that's-
discontinuous.
That's when I was confused. I thought we said we had it at 5.
Ah.
Like, how is it at 1? Okay.
Great. Okay. Let's look at some other graphical examples. Let's look at some equations. All right, looking at A. Where's the discontinuity in A? X equals 2. Great. How do you know that? Because the function is undefined there, right? Can't have continuity if the f of a doesn't exist, or if f of a is undefined, right? Okay. B.
What is it? Why wouldn't?
It's not 0.
Yeah.
It's the value that was in the denominator, 0.
X equals 0 is the problem.
I told you X equals 0.
So what's going on here?
Oh, but it says I can't.
And if we look at this, we know that this does not exist, right? We looked at this one in a previous, I think in 2.2 we looked at this and talked about why it doesn't exist. So again, for us to have continuity at a point, the limit has to exist and it has to equal f of a, right? So here the limit doesn't even exist at 0, so how can we have continuity at 0? We couldn't. It depends on the question, what it asks for. How about C? You think 2. Why do you say that?
But it can't equal 2. I think that's why it can't. Isn't it not? Isn't it just?
Well, I noticed that the numerator of that factors, right?
Yeah. Oh, so that is it the X equals 2 what?
Direct substitution.
Oh. Okay.
And that's not f of 2, right? Because what's f of 2 equal? 1. Right? So x equals 2 is our answer. That is discontinuous there. Certainly.
So is the top part just how you prove it then?
Yeah, that was me just checking because looking at that, I couldn't tell.
Yeah.
It's like, maybe it is, maybe it's not. I don't know. 2 would be your candidate, though. Well, x equals 2 is the location, right? That's where the discontinuity is. So I'm checking at 2. The limit as x approaches 2 is 3. F of 2 is 1. Those disagree. That's why I have discontinuity at x equals 2. Is that?
Yeah.
You know, this is going to look like, you know, it's going to look kind of like this part. That's what that would have looked like, right?
So f of 2 is like
That's the y-coordinate, right? The y-coordinate of the function when x is 2. So again, if we looked at these pictures, in part A, we had the open point. Again, that's going to be discontinuity. In part B, we have that infinite discontinuity, that asymptote. Part 3, we have like that jump discontinuity going on. And then this one we didn't look at because I didn't talk about the Heaviside function. I think is what that is. Okay. So one thing we have to be careful about is if you think about way back to like algebra 2, if I look at the function like y equals the square root of x, remember what this function looked like? Looks something like this, right? Now I could draw that without having to pick up my pencil. What's the problem? Are we continuous at this point? What's the left-hand limit? It doesn't seem like there is one. So we need to kind of adjust what we mean by continuity if it's at an endpoint. Okay? So we're going to make a little adjustment here. So we're going to refine our definition. We're going to say a function f is continuous from the right at a number a if, the right-hand limit is equal to f of a. And we're going to say that f is continuous from the left at point a if the left-hand limit is equal to f of a. So what we'll do now is we're going to say then a function f is continuous on an interval if it is continuous at every number in the interval. And here we make our little adjustment saying if f is defined only on one side of an endpoint of the interval, we understand continuous at the end point to mean continuous from the left or continuous from the right. So what we're saying is if you want to be continuous on the interval like 0 to infinity, here we just need the right-hand continuous to call that interval continuous over the whole thing. Because it's not continuous at 0 if we look at it with our strict definition of continuity. But here we're saying if it's on an interval, you're looking at the start or the end of the interval, you really only need one side of continuity, and that's going to be what we really want. Because again, something we could draw without picking up our pencil, right? So you want to be able to have a situation like the square root of x. We want to be able to call that continuous. And the issue is just, what do I do at that start point? Because that doesn't seem like it fits the definition of continuity, because there's no left-hand limit to that. And all we're going to say is, if you're doing it over the interval, if you have an endpoint, you'll need one side of it to be the limit to work, and then it's fine. Okay. So yes, go ahead.
Oh, it only just really continuous on like one side. It's like right or left.
Correct. Well, I mean, you need like right-hand continuity from the left end and then the left end continuity for the right end. So let's look at an example. Okay. So if I want continuity on this interval, I have to show continuity at a point for every point on that interval. So I'm going to start by taking some a from the interval. Actually, we should do this. Let's use the open interval. And then we'll check the endpoints separately, because the definition for the endpoints is different than our definition for the meat of the interval. So the limit as x approaches a of 1 minus this is equal to, I use my limit laws. And I get this, right? Is everybody okay? What do you notice about this? It's the same thing, just with an A plugged in, right? What does that mean? It's just f of A, right? All I did was plug A in. Well, we still have to check where A equals -1 and A equals +1. We have to check the endpoints also for continuity. So if I do that, what am I going to get? 1, which is the same thing as f of -1. And if we look at A equals 1, what do I get here? Still 1, which is still just f of 1. Now we're done. So we showed continuity in between the endpoints, and we looked at the continuity at each endpoint. That covered the entire closed interval. Well, no, -1 coming from the left would be the stuff less than -1.
Oh.
Right? You want the stuff bigger than -1. That's from the right. So the left endpoint, you're always looking at the right-hand limit. And the right endpoint, you're looking at the left-hand limit. Right. Because you only care about what's happening in between the endpoints on your interval. Here's a lovely, 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 lovely theorem for us. It says that if f and g are continuous at A and c is a constant, then the following functions are also continuous at A. If I look at the sum of two continuous functions, that's continuous. The difference of two continuous functions is continuous. A constant times a continuous function is still continuous. The product of two continuous functions is still continuous. And the quotient of two continuous functions is still continuous, assuming that the denominator is not 0 at the point in question. So far, so good. Here it gets even better. Theorem 5 says that any polynomial function is continuous everywhere over its entire domain, -infinity to +infinity. So is a polynomial continuous at A, at a point A? Of course it is. How do you prove it? You quote Theorem 5.
Just call Theorem 5.
Well, or you can just say, theorem states polynomial is continuous everywhere, right?
It doesn't have a name.
You don't have, no, it doesn't have a proper name. Okay, part B says any rational function is continuous wherever it is defined. It is continuous on its domain. So if I take the product of two rational functions, what can I say?
Continuous.
It'll be continuous over the union of those two domains, or the intersection of those two domains, I should say. Right? A rational function is a polynomial divided by another polynomial.
Oh.
Okay?
So all like the example 5 is
Rational.
rational.
Yeah, of course.
Example 1. Oh, that's rational. When it's I don't know how long it's continuous. It's with this is always continuous.
Okay. So, what do I have here? There's a rational function, correct?
Yeah, so it's continuous.
So I know it's continuous. So what does that allow me to say? That this limit that we're asked for is equal to f of negative 2. So what am I doing here?
Oh, you
Just doing direct substitution, right? It justifies us doing direct substitution.
So the fact that it's continuous is equal.
Yeah. So Talika said this, I don't think everyone heard it. Because we have something that's continuous, we can now do direct substitution on that. So, but remember before when we were just kind of like doing the stuff with the radicals and it was like, yeah, it's okay to do this. Like, remember, we're doing like 3 limit laws to do this. This now justifies us just doing a direct substitution on almost anything that we're going to work with, right? We have to be a little bit careful that we're not plugging in somewhere where we're discontinuous. But basically that gives us the tool that we need. Theorem 7. The following types of functions are continuous at every number in their domain. Polynomials, rationals, root functions, trigonometric functions, inverse trigonometric functions, exponential functions, logarithmic functions. Pretty much everything that you've worked with to this point is continuous over its domain. You'd have to use a piecewise. So, if we ask here, where is this function continuous? Okay, well, how am I going to figure that out?
0.7.
Nope.
0.5.
Nope. We're going to look at each one of these pieces separately, right? What's the, so what's the domain for the natural log? Well, this is something we should remember from Algebra 2 and or pre-calc. I know, and I taught you pre-calc, so you can't blame me I can't blame myself on this one. Okay. What numbers? Shh. What numbers can't you take the logarithm of? Correct. Well, you can't take 0 either. But, so, yes, that's 0, comma, positive infinity. Okay? Inverse tan. What's the domain for inverse tangent? There you go. Why is it negative infinity to positive infinity? What's the graph of tangent look like? Looks like this, right? Inverse tangent is the same as the range for tangent, which is all real numbers, right? Because you have an arrow pointing down, arrow pointing up. And then, what's the domain for this? Everything other than -1 and 1, right?
Oh, wait.
Okay. So if I take the intersection of this stuff, what is my domain going to turn into then? This guy doesn't matter, right? Because that's everything.
Yeah. Wait. Would it just be negative? 0 to positive?
Well,
Negative?
Oh.
The last one.
0 to 1, yup. Excellent. So if we look, this can't be in there, right? Because that's not in the domain of this. There's no overlap between those, right? The overlap between this and this is 0 to 1. And then the overlap here and this is the entire 1 to positive infinity.
It's only where it overlaps.
Yes, intersection is overlap. Yeah. Okay, intersection is overlap. What's the overlap between numbers less than -1 and the numbers greater than 0? These are the numbers less than -1,
Yeah.
and this is the numbers greater than 0. What's the overlap between those? Nothing, right?
Yeah.
So we got nothing there. What's the overlap between the numbers -1 to 1 and the positives? Stuff greater than 0. Okay. So if you're confused, this is what you should do. Okay? Number line.
Yeah.
So 0, well, let's say -1, 0, 1. Okay? So we'll color code this. This will be red. This will be green. And then this will be blue. So I have red. I have green. And I have my blue. Okay? So the overlap between all three of these lines happens here and here. 0 to 1, 1 to positive infinity.
Okay.
Does that visual helps?
Yeah. A lot.
Yeah, do that then.
Okay.
Do that no, it's not child terms. We're doing the exact same thing. Instead of just talking about it verbally, we're doing it pictorially. It's not a lesser version of it. It's the exact same communication. Just sometimes some of us are better with pictures, some of us are better with words. Shh. It's not dumbing. It's not. I literally believe this. It is an equivalent representation. It is not dumbing it down. It requires more writing, but so what? So what? It's not. Stop saying it.
It's for like drawing pictures. It's shit colors in my.
It would actually be harder for someone. Yeah,
All right. Shh. So we still have a little bit more to do, which is fine. But I think we can do, well, we can do up to a lot, right? Hold on one second. Okay, so we can do up to like 40, like up to 49 is all still good. Like up to 49, we've done enough. 49 and above, we haven't quite got to. Yeah, don't worry about 54 because we haven't talked about the intermediate value theorem. But you guys should be able to do up through 45. And remember, if you didn't do the multiple choice questions, try to find yourself 20 minutes or so to grind those out. Try not to, you shouldn't spend more than 20 minutes doing it. You know, like 2 or 3 minutes a question is fine, okay? Don't take like an hour. You don't need to do that, you know. It's just to get us thinking. Something we'll talk about in next class.